Hi, and welcome to Allen High School's discussion of chemical bonding at the APIB level. We're moving into metallic bonding structures, and we briefly talked about this in pre-AP, and we're not going to go into it in much more depth, honestly, but we are going to add some mixtures to the mixture, so to speak. Okay, metallic bonding also involves long range, regular predictable arrays, much like network covalent. But that's kind of where some of the similarities, I guess I can't talk today, end. Sorry, predictable array. Okay, now metals are typically described, and this is just one of the models, but they're typically described by what's called a delocalized electron model. If electrons are delocalized, that means they're not fixed to a particular location. And sometimes we call this the sea of electron model. I like to think of it as like a little commune. Okay, let me show you what I mean. So what we have here is in these lattice points, you have positive ions. If you envision like the lattice fences that you see sometimes people's yards, so or on the back of a deck or something like that, those lattice fences that crisscross. So if we drew lines through this like this, you see that there are points of intersection. Each of those points would be called a lattice point. So right here we would have a lattice point, and here we would have a lattice point if I'd drawn it right. There we go, a lattice point. Now, at those lattice points are the positive metal ions. Okay, and the blue represents these valence electrons that are swimming around. So those valence electrons can hop from house to house, and we always know that the other moms are going to take care of the kids, and they'll eat at their house, and then the next night they'll spend the night at the other person's house, and they're just moving all along the little neighborhood freely. They're not trapped into a particular location. They are delocalized. Metal ions, let's go back to some of the terminology, are arranged in a lattice, and the valence electrons are free to move. Now, I'm focusing on structure. In the next unit, we'll talk quite a bit about function, but freely moving electrons is by very definition electricity. And so this ability of electrons to move freely is why metals conduct electricity. And we'll come back and revisit that again. Now, again, these are not discrete beginning and ending molecules. If it's a metal, it's going to depend on where I grab those metal wire clippers and cut it up. And that's where it's going to end. Now, an alloy, and this is an important addition to the AP curriculum. An alloy has a metallic solvent. Recall that a solvent is present in the greater amount, mixed with a solute. Now, sometimes that solute's another metal, and sometimes that solute is not another metal. So it's not necessarily a metal. Bronze is copper with tin or aluminum. Brass is copper with zinc dissolved. Now, definitions, just like remember we calculated molarity is moles per liter for a solution. Solutions can have all varying compositions. And that is true of alloys as well. They do not have a constant composition, and they're typically represented as parts per million or percent by mass. A part per million would be your mass of your solute over the total mass. And instead of multiplying by 100, you multiply by like 1,000,000. I wish I hadn't done this because now I'm going to get it wrong. But parts per million. Okay, so we multiply by 1,000,000. Okay, I don't deal with parts per million very much, so sometimes I forget, but I think I got that right. All right. In substitutional, and yes, you do have to not only recognize these alloys, you have to recognize, you have to be able to look at a representation and understand which one we're talking about. So you have to recognize them by term as a definition. You have to recognize them by some sort of representation. And you should be able to draw some sort of representation of these. In substitutional, as its name implies, substitutional. Okay, let me write that down. Well, there we go. The solute metal substitutes for or replaces a solvent metal at the lattice points. Okay, so if I could go back to this picture, we have this lattice point. So a substitutional one would replace metals at those lattice points. Okay, and that's what's being shown right here is a substitutional alloy. So notice that in place of this, we have a blue one put in there. Okay. Now, we also have something that's got a little bit more complicated name, but it relates to how we describe lattice and crystals. It's called an interstitial alloy. Steel with carbon atoms is in the interstices of the in-between points. Inter, kind of between, in that sense. So do you notice here that none of the red ones have been replaced? None of them are substituted. Instead, what we have is the solute is in between in what are called the interstices of the lattice structure. Okay? It's not replacing. If you notice, we've got the same number of our parent solvent metal here as we have here. It didn't replace. It snuck in between. Now, there's also combinations. And the goal is we want a particular function or structural quality of our alloy. And so scientists and chemical engineers design different mixtures or different alloys to get the properties that they need. So here's a combination one. Those are some examples for you. And you should be able to recognize every one of these and describe what they are. And in the later unit, we will talk a little bit more about the functioning of it and how having an alloy alters the function of the metal. But until then, we're focusing on structure. And our next one is ionic. So until then, this is signing off.